Okay, good morning, everyone. First of all, I would like to thank the people from the Academia Sinica and the people from Formosa Group and people from the Nikiso for giving me this opportunity. So I'm very happy to discuss with you, especially with the young researchers. So today, I'd like to explain the same material, that is the gallium nitride, but I'd like to change the title a little bit. This material system is very, very important for establishing a new society, that is the sustainable and smart and safe society. So I'd like to explain more and discuss with you. Okay, but before starting this presentation, I'd like to say that we are very happy that the Professor Tasuku Honjo received the Nobel Prize for in physiology and medicine. The reason why I'm so happy is not only because he's Japanese, but his finding of the fundamental research leads to the big business, big market. So which is very similar to the blue LED story. So that's why I'm so interested in his receiving the Nobel Prize. Okay. Okay, let me start with the blue LED story. Why and how the blue LEDs was developed in Japan. This summarizes the history of the development of LEDs. The first LEDs was commercialized in the early 1960s. The material is gallium, metallic gallium and arsenic and phosphide. It's a compound. Okay. The first one was the LED LEDs. And then in the early 1970s, the green LEDs was commercialized. The material is the metallic gallium with phosphorus. Okay. So if the people studied the quantum mechanics, it is very easy which is next. Okay. If we look at the periodic table of the elements, okay, gallium and arsenic for red LEDs, gallium and phosphorus for green LEDs. So it's like a series. Okay. So next should be the gallium and the nitrogen for blue. So in 1970s, many researchers all over the world tried to commercialize the blue LEDs based on gallium nitride. But unfortunately, in 1970s, all the efforts were in vain. It was very difficult to grow high-quality crystals, and there was no P-type gallium nitride. And the blue emitting layers, indium gallium nitride, it is impossible to grow. So the world's top scientists tried but abandoned the gallium nitride LEDs in 1970s, except one person. His name is Professor Makasaki, my supervisor when I was a young student. I would like to emphasize that he read the invention of gallium nitride-based blue LEDs in Japan. He has a strong belief to this material, gallium nitride. And also, he always encouraged the young student, young researcher like me. Let me explain more details. He started the gallium nitride research from 1967. It's already 50 years ago. Okay. First, he used the sublimation for the crystal growth, and he changed the method to MBE. It's a molecular beam epitaxy, and then he switched to HBB. It's a hydrogen transport vapor phase epitaxy. At the Matsushita, it's a private company. Now it's Panasonic. But unfortunately, the manager of Matsushita thought that it was too difficult to commercialize this material system, so they abandoned the project, research project. So he had to move from the private company to National University in 1981. And he decided to start the new crystal growth method. That is MOVP, the metal organic vapor phase epitaxy. Okay. Professor Akasaki, always encouraged us by saying that you are the best person who knows MOVP growth of gallium nitride, because of course the students did perform the experiments. Okay? So I was always motivated with his encouragement. So I could continue the research or experiments for a long time. The 3 years as an undergraduate student and the first year of master courses and second year of master courses, 3 years, I finally succeeded in growing world's highest quality gallium nitride at that time. There was a very important hint from the previous professor. Before Professor Akasaki became the professor of semiconductor in Nagoya University, Professor Tatao Nishinaga performed the experiment, and he grew BP on silicon. Okay. BP is not a petroleum company. Okay, it's a material, boron phosphide on silicon. And the young professor of the Akasaki laboratory, Professor Sawaki, always discussed with the young people like me. And he taught me the story of boron phosphide on silicon, which was a very, very good hint for me. So applied the idea to grow gallium nitride on sapphire. It's a low temperature buffer. Then finally I succeeded to grow the world's highest quality gallium nitride at the time. Then I decided to become the PhD candidate. So I tried to enter the doctoral course. But during my doctoral courses for 3 years, I concentrated on seeking P-type gallium nitride, although all the efforts were fruitless. So I could not get PhD in 3 years. Today, in Japan, the university, if they don't have the PhD, they never become the research associate. But now, at present, at that time, I was very, very lucky that I could continue the research as a research associate. So I got the support from the Professor Akasaki. Okay. So I could continue the research on P-type gallium nitride. And then finally, I succeeded the world's first P-type gallium nitride PN junction in 1989. So we could grow the gallium nitride, but we need a special treatment it's a low energy electron beam irradiation treatment. But at that time, we didn't have the equipment for the treatment. The Toyota Gosei, it's a collaboration company, they have that. So, taking 1 hour by scooter, I went from Nagoya University to Toyota Gosei, and then it took 7 hours for treating one sample. And then we went back to Nagoya University. Then characterize or measure the properties. I was intense in this research, so taking total 9 hours did not bother me at all. Then finally I could write the journal papers and I could get the Doctor of Engineering with this journal papers. Okay. In 1989, I appeared in newspaper behind Professor Akasaki. He is Professor Akasaki and this is me. It's aged 29. And then, a quarter century have passed, 2014. So let me explain what had happened in 2014. Okay, I was aged 54. Maybe you know that this week there is an announcement of Nobel Prize. The Nobel Prize award ceremony always be held at December 10th. That's the ceremony of Alfred Nobel's death. But 2 months before, always there is an announcement. Okay? The reason is, we have to prepare a lot of things, so we need two months to prepare. So in 2014, the announcement was held in October 7th. Then 1 month before, in September, we went to the laboratory trip near Mount Fuji. Please pay attention to this photo, okay? Yeah, 2014, these 3 persons received the Nobel Prize in physics. He is very famous. He had been nominated as the candidate for Nobel laureate for more than 10 years. And he was also extremely famous. So these 2 persons prepare the announcement always. But this person is nameless. So let me explain what had happened. Every year in early October, many journalists came to our office because we are collaborating each other and waited for the announcement of Professor Akasagi winning Nobel Prize. And always, every year, journalists requested me the very nice comments, okay? So I have to wait for the nice comments to Professor Akasagi. I enjoy such a situation, but 3 years have passed, 5 years have passed, 7 years have passed, and 10 years have passed. And every year, the journalists request me the same thing, the nice comments. So I was really tired of such a situation. So I decided to go abroad without informing to the university. And the announcement was done during my flight from Nagoya to Frankfurt. Well, Frankfurt was a transit. So I opened my PC and found that I received plenty of emails entitled "Congratulations" or "Omedetou gozaimasu" in Japanese. But no one wrote the reason why. So I didn't understand what had happened. I should not have received such a large amount of emails, so they should be a spam mail. So with fear, I went to the Rion, the final destination, and found many journalists waiting for someone. So I thought, oh, I am very lucky that some famous movie star is coming with the same flight. But who? And then one of the journalists came to me and said, you received the Nobel Prize. Wow. But the trouble happened in Nagoya University. The mass media interviewed my laboratory staff without me. So this is my photo. Also, I was missing at the press conference in Nagoya University. Okay. Yeah, let me explain the reason why the blue is so important. Only the blue can realize white. Other colors, red LEDs or green LEDs, cannot realize the white. Yeah, I have a small demo. This is the blue LEDs, and only the blue LEDs can realize white with this phosphorus. Even though we use the phosphorus, we cannot realize the white. That's the reason why the blue is so important. And now, according to the database company, by year 2020, over 70% of the general lighting will be replaced to the LED lightings, by which we can reduce the total electricity consumption by about 7%, which corresponds to the 1 trillion Japanese yen per year by year 2020. And more importantly, gallium nitride-based LED lightings help people to escape from darkness. According to Nobel Foundation, LED lamp holds great promise for increasing the quality of life for over 1.5 billion people around the world who lack access to electricity grids. Due to its low power requirements, it can be powered by cheap local solar power. I really recognize this phrase when Mr. Gantumu, the Minister for Education and Science of Mongolia, visited us and gave me the word of gratitude. The reason is, according to him, for Mongolian people, the traditional lifestyle is the nomad life. Using the tent called gel, they moved around when the season changes. But the life is very tough, very difficult to continue. So the young generation, young people, Mongolian people, do not want to continue the nomad life anymore. So they want to have the fixed housing. That's the social problem, he said. But the emergence of LED lamp changed the mind of young Mongolian people. So I visited one of the young Mongolian people who continue the nomad life, and I really found that they use the LED lamp. I was so happy to see that. This is my blue LED stories. And after that, I changed the research subject from blue LED to blue lasers, and then it is finished. So I search for the new research subject. There's my turning point from blue to UV. So as an internship, 3 months internship, I visited Sandia National Laboratory, Albuquerque, New Mexico, in the United States, when I was aged 38. Yeah, before visiting Sandia National Laboratories, I had thought that I would be superior to them in terms of blue LEDs and gallium nitride research because we already have done the blue LED and blue lasers. But when I met with them, I found my mistake. During 3 months sabbatical at Sandia National Laboratories, I learned a lot about very high creativity and sincerity of Sandia National Laboratory researchers. So I changed my mind. I hardly decided to contribute to mankind even more than them, but how to? So I tried the new subject, that is the UV and the deep UV LEDs. You know that the Earth is the water planet, but the water we can use is very, very small amount. For example, the fresh lakes water is only 70 ppm, and the rivers, it's only 2 ppm of the total the water on Earth. And more seriously, still more than 660 million people lack access to improved drinking water sources, and 2.4 billion people. 2.4 billion people do not use an improved sanitation facility. And more seriously, the climate change or the global warming causes increase of bacterium and vírus in drinking water. So how to get the safe water is one of the primary issues for us. So for the young researchers in Japan, the most difficult issue is how to get the research fund. I was very lucky I could get a fundamental research fund from Ministry of Education and JSPS, Japan Society for the Promotion of Science. But to tell the truth, the amount of total research fund was not sufficient to purchase, to buy a new equipment for crystal growth. So we designed by ourselves, but it was still very expensive. So I went to the company, Epic West, the new reactor provider. So finally, they agreed to supply us the new reactor with a very, very reduced price. So I could start the research. And also, we have the problem of the spare parts. For spare parts, we have to use a very special material. This is tantalum carbide for high temperature growth. But they are also very, very expensive. So I went to the company Ibiden, and they supplied their research grade spare parts with the free of charge. So I could succeed. We could succeed to grow the high quality aluminum gallium nitride. Then, as the next step, we tried the Upright Research Fund, Ministry of Economy, Trade and Industry. It's called NEDOC. It's a big fund. So we succeeded the PN junction and high out power UV LEDs. And then finally, the Nixo and the venture company UV Craftery succeeded in fabricating or manufacturing the deep UV LEDs, the emitting from 265 to 350, which is supported also by the private bank. Okay. This figure shows the external quantum efficiency of aluminum gallium nitride-based UV LEDs. There are two trends, gallium nitride template and aluminum nitride template. So the peak efficiency is around 280 nanometers. Let me explain the details. Yeah, which process limits the efficiency of deep UV LEDs? There are mainly three terms. One is the internal quantum efficiency. It's a ratio of the carriers injected into the active layer recombine to emit the light. It's internal quantum efficiency, IQE. And how much carriers can be injected into the active layer? It's and injection efficiency. Okay? Injection efficiency. And the third term is the light extraction efficiency. Because the semiconductor material, the refractive index is higher than 1. The air is 1. So not all the light can extract from the semiconductor to the air. So which is called the light extraction efficiency. These three terms, internal quantum efficiency is related to the crystalline quality. Carrier injection efficiency is related to the p-type hole concentration in aluminum gallium nitride, and the light extraction efficiency is related to the LED structure. Okay, first, to grow the high quality aluminum gallium nitride, we need a high temperature growth. Okay? This is the dislocation, the defects. With increasing the growth temperature, dislocation can be minimized. That's the first point. So, by reducing the dislocation density, DD is a dislocation density, the IQE can be increased. Okay? So, according to the shock-radiated hole model, this term can be minimized by reducing the threading dislocation density. That's the one thing. And the second term, hole concentration. It is not easy to increase the hole concentration. There is the fundamental limit. For example, the gallium nitride, we can reach the hole concentration over 10 to the 18th, but 50%, it's only meet 10 to the 15th. So we should clarify how this low hole concentration affects the performance of the DPU LEDs. So we compared these two different types of structure. One is it's a current injection, and the other is photo pumping. Okay. The photo pumping, we can expect the injection efficiency 100%, but current injection it's lower than 100%. So if we compare these two, we can estimate the injection efficiency. And our result is shown here. With the same carrier injection, the efficiency is different like this. So if we compare these two, we can expect the injection efficiency, it's only 30%. And for light extraction, we have the very serious problem. In this device, there's a deep UV absorber, P-type gallium nitride and a P electrode, which has absorbed the deep UV light. So one of the colleagues, our colleague, Professor Ono, tried the different approach. He is using a carbon nanotube for transparent electrode. And he succeeded to control the operating voltage like this. In such a way, the Nixo demonstrated the commercially available water purification system like this. Okay? Yeah. This system is very, very good. And I'd like to explain in more details. There are 5 factors influencing the performance of water purification. We need a highly intense UV LED chip. So Nixo chip is very, very intense. Okay, so it's okay. And how to elongate the exposure time? The system is like this. The water is in and the water is out. water is in and water is out. So there's a long exposure time. In addition, they use fluorocarbon. Fluorocarbon is UV reflected material. So they can get the sufficient exposure time. And also, the transparency of the water is very important. For example, if the transparency is 95% for 20 centimeter system, the intensity decreases to around half. But if the transparency of the water is only 70%, it's only 1%. So I should say that the purification of wastewater is very, very difficult. So we need to clean up or filter the water. And also the weakness, it depends on the bacterium on the virus. For example, the Combacillus or Legionella or Cryptosporidium, it's very weak. So with a short time exposure, we can deactivate this bacterium. But norovirus, adenovirus, or influenza virus, the flu, it's very strong against the DPV lethal. So we need a long time to deactivate these bacterium. Also, as I showed you before, the intensity of the efficiency of LEDs drops gradually when shortening the wavelengths. And absorption of DNA or bacterium becomes maximum at 265 nanometers. So there is the optimum wavelength for deactivating the bacterium. It's around 280 nanometers. Then the next step, we need to consider the reliability of the DPV LEDs. So we are collaborating with the University of Padova, Italy. The Professor Enrico Zanoni, he's a specialist on investigating the reliability issue of the semiconductor devices. So, according to them, according to the Padova's results, other commercially available UV LED, there is a deep level emission. In comparison, Nikiso's deep level LED, there's no deep levels. Also, temperature dependence of the efficiency is quite different. Other commercially available UV LEDs, if the temperature increased to 70 degrees or 80 degrees, which is very usually occur because of the high density operation. But in other commercially available UV LEDs, the efficiency is less than 50%. But the Nikiso's LEDs, it's over 70%. So we can operate the Nikiso's LEDs very, very safely. And it's very reliable. And the application of the DPV LEDs is expanding a lot, not only for water purification. This is the oyster. I don't know whether the Taiwan people eat the rare oyster. Oh, really? Okay. So if so, maybe you already eat the oysters, rare oysters which is purified by the DPPLEDs. But not only the water purification, it can be used as the sterilization, resin cures, paper money discrimination, and dermatology, treating the skin disease. You can use the DPPLEDs to treating the skin disease. And also, it can be used as a photolithography, more precise patterning compared with the blue LEDs. Okay. So I would like to mention that I visited the Stockholm the Nobel Museum in September 21st this year and found that Nikiso's DPPLED, the demo is just beside the entrance. It's a top demos in the Nobel Museum. So you can also see our the chair. At the back side of the chair, there's a sign. So I found our signs here. So if you have the chance to visit the Nobel Museum, please see this demo. You can see just at the entrance. You can see the Nikiso's demos. Okay. So, using the remaining time, I'd like to explain what we are doing now. We are doing to establish a new transformative electronics for realizing Internet of Things and Internet of Energy. Maybe this word is common, the Internet of Things is common, but this word, the Internet of Energy is not so common. So let me explain what the Internet of Energy means. Okay, what's the transformative electronics? The role of electronics is transform the energy. Okay, for example, the photovoltaic panel, the solar panels, solar cell panels, which transform the photon energy to electrical energy. Okay, and the LED lamp transform the electrical energy to photon energy. So the law of electronics is transform the energy. Okay, and our goal is we are aiming at transformation efficiency over 100%. Okay. If the high school student writes this, you cannot get to the point. Okay, but let me explain why we said that the over 100% is possible. Okay, for example, the solar panel, the power efficiency is less than 50%. Even though we use the multi-junction stack structure, it is difficult to exceed the efficiency over 50%. And the display, today's display is more serious. Power efficiency is less than 5% because we have to use the color filters. Okay. The backside, the white light source is used. So, in case of the LED colors, blue and green is cut. That's why the efficiency is so low. But if we look at some new movies and new TV shows, mental energy is countless. Okay, that's why we can realize over 100%, including the mental energy. Yeah, it's half joking, but half serious. Let me explain more serious thing. This graph shows the CO2 emission by electricity generation in Japan. Total CO2 emission is decreasing in Japan. But due to the big earthquake attacked East Japan in 2011, and we have to stop the nuclear power plants. So the ratio of coal, LNG, and oil, the fossil fuel, increased from 62% to 87%. That's why CO2 emissions increased 19% from 2005 to 2015. According to the government, he can continue the 3 years of Prime Minister. The Japanese government plans to target an 80% cut in greenhouse gases by year 2015 from the current level. It's a very challenging target, but how to do that? According to Bill Gates, he's very famous Bill Gates. According to him, the total amount of CO2 emission is written in this formula. Okay? It's a mathematics. So if one of the terms can be zero, the total should be zero. It's a multiplication. Okay? It's easy the mathematics. But these two terms, the population is increasing all over the world. And also the service per person. Service means the vehicle, TVs, and so on, which is also increasing. So these two terms are increasing and difficult to be zero. And also the final term, CO2 per energy. Of course, we can realize the CO2 per energy to zero using the renewable energy source, but it's not sufficient. So we still do not find the sufficient energy which does not emit CO2 and safe after use. The waste of nuclear material which is not safe. So only this term, energy per service, we can reduce by innovation. Okay. Yeah, LED is very, very effective to reduce the total electricity consumption, but the ratio of lighting for electricity is only 14%. More important is air conditioners and refrigerators. It's close to 60%. So we have to reduce this term. This is the motor control, okay? And as for the motor control, the inverter circuit is very, very effective. This is the inverter circuit. This graph shows the input power and airflow of air conditioner. Compared with the mechanical damper control, we can reduce the input power by using an inverter, which is close to ideal value. So inverter control is very, very effective. According to Daikin, Japan already realized 100% inverter control. I don't know much about Taiwan, but the EU is still less than 50%. And the United States is very serious, only 11%. But even using the inverter control, there is some problem. Okay, let me explain how we lose the electricity from the solar panel on top of the roof of your home to operate the PC. We have to use the power conditioner. The solar panel generates the DC power, but at home we use the AC power. So we have to transfer the DC power to AC power. So we need a power conditioner. It's 5.5% both. And inside the home, we use the switching regulator. Oh, I hope. This one. This one is relatively warm. the warm means we lose the electricity. It's a 7% loss. And inside the PC, we have to change the DC voltage. At least 2 DC-DC converter, it's 5 and 12% loss. So in total, even though we generate 82 watts, we can use only 60 watts. So about a quarter of generated power is lost. So we have to reduce this loss of energy. We can do that by using the blue LED materials. Okay? The reason is blue LED materials is 10 times or 40 times stronger than that of conventional silicon. So we can reduce the size of the device to 1/10. So the loss is 1/10. Okay? The power gallium nitride is a unique solution for high power and high switching speed. This figure shows the operating switching speed as a function of the switching power as a function of operating frequency. If we can fabricate high operation frequency, we can realize everything with this material. Why we need a high switching speed? We can reduce the size of the system, size of the circuit, so we can reduce the weight of the system. So gallium nitride device can be used in every application if the cost is sufficiently low. So we can reduce the total electricity consumption by about 10% by replacing conventional silicon-based transistors to new gallium nitride-based transistors. And also, wireless information transmission, the gallium nitride-based device is a unique solution for high power and high frequency. The ratio of wireless communication will exceed 84% by year 2020. And also, for 5G communication, we need a very quick response between, for example, vehicle and the server. The reason is, for autonomous driving, still we have the problem of the PC capacity. So we have to connect to the big server, okay? But when you drive on 100 kilometers per hour, if the response speed is low, it's very serious. There should be a lot of traffic accident occur. So to suppress the traffic accident, we need a very quick response, less than 1 millisecond. Okay. Also, we need a lot of clients for Internet of Things. It's more than 1 million clients per square kilometer. How to do that? We have to increase the carrier frequency, and also that we have to expand the bandwidth. Okay? At each channel, we need the same electric power. So if the channel is increased, we need a high power. So the expanding the bandwidth means that we need a high power. High power and high frequency is essential for the 5G communication. And only this material, gallium nitride, can realize high power and high frequency. That's why I said that it's a unique solution for high power and high frequency. So, gallium nitride device for wireless information and the wireless power transmission connecting at any time and place. It's the Internet of Things and Internet of Energy. Let me explain what is the Internet of Energy. This is a demonstration of wireless energy transmission. This is the power supply, and this is disconnected with the wire. It's wireless energy transmission. Okay. So this board receives the energy to operate the LED lamps. It's very feasible. Even though we change the position, it's still connected. Okay? And this is the capacitor connection. So if there is another dielectric material like human is inserted, it's all automatically disconnected. So it's very safe. So using this technology, we can realize to transmit electricity to emergency helicopters, disaster rescue robot, power assist robot, healthcare, industrial robot, electric vehicle, and even drone. We can transmit the electric energy to drone, to a flying drone in future. Okay, from now, let me explain a little bit detail of the specific feature of the nitride device. We are using the high electromobility transistor structure. The common HEMT structure is based on the gallium arsenide. Gallium arsenide is a highly pure material, and for barrier layers, aluminum gallium nitride, we dope impurities. Okay, so if we try to operate high current, we have to dope a large amount of impurities in the barrier layers. But unfortunately, the low mobility channel is formed here, so which degrade the performance of the HEMT in case of gallium arsenide. In comparison, nitride, we don't need to dope impurities. We can use highly pure materials. Okay, so the idea is first pointed out by Professor Michael Schultz, the Rensselaer Polytechnic Institute. Okay. Yeah, we are using the idea of superjunction. Superjunction. The superjunction means if we use the highly pure materials, we can operate high voltage. But unfortunately, the resistivity increase, so the current is limited. And if we dope impurities, we can reduce the resistivity. But also, the operating voltage has to decrease. So to overcome this trade-off, the idea of superjunction is demonstrated in silicon device. The idea is like this. Donor impurities and acceptor impurities doped separately. The point is, the concentration of acceptor and donor should be precisely, very precisely the same. In case of nitride, it's automatically realized because we use the polarization. Okay, piezoelectric and spontaneous polarization, we can induce two-dimensional electron gas and the opposite side, two-dimensional hole gas, just the same concentration, by which we can automatically realize the superjunction structure. So we call it polarization superjunction or PSJ structure. Okay? Yeah, compared with the conventional HEM structure, we use this layer. It's unwrapped gallium nitride and the thickness is only 10 nanometer. Only with or without this layer, the performance changed drastically, like this. In the normal HEM structure, the operating voltage is less than 100 volts. But by using PSJ structure, we can increase the operating voltage over 1 kilovolts. Now, we succeeded in fabricating the very high voltage HEM structure over 10 kilovolts, which is the world's top class, the high voltage devices. So we apply this technique to operate the new electric vehicles. Supported by the Ministry of Environment, we try to fabricate a new inverter system for electric vehicles. Electric vehicle, we need output power over 100 kilowatts. But conventional silicon IGBT, insulated gate bipolar transistor, we lose 3 kilowatts. But our colleagues, Professor Yamamoto, succeeded in fabricating a gallium nitride inverter efficiency over 99%, almost 100%. So the loss should be less than 1 kilowatt. But the problem is, at present, the output power is 1 kilowatt because he uses the highly dislocated devices. So now we are trying the 100 kilowatt per chip device for new concept of the vehicle, that is all-GaN vehicle. All the electric circuits were based on the gallium nitride inverter, gallium nitride DC-DC converter, gallium nitride onboard chips, and gallium nitride LED and laser headlight. Our dream is to drive this all-GaN vehicle at Tokyo Olympics 2020. But to tell the truth, it's not easy. Not the technical problem, but there are very severe regulations in Japan. This kind of vehicle, we need a long run time for getting the permission. Okay, so how to propel innovation? When I visited Silicon Valley and talked to the people that in case of blue LEDs, we need, it took 30 years from the fundamental findings to the market size exceeds 1 trillion yen. So when I talked this, one of the very famous investors, Mr. Sumida, the world's capital partners, he claimed to me, investors cannot wait for 30 years. It should be no longer than 10 years. But how to do that? So we started the new organization, the Consortium for Gallium Nitride Research and Application. It's an open innovation platform Up to now, 47 private companies, 20 universities, and 3 national research institutes join our consortium. It's accumulation and application, leading-edge research outcome. The aim of this organization is to connect the decibel line from the seed to the commercialization or business. Okay? According to the NASA technology readiness level, we tried not the 1 to 9, but 0 to 10. Okay? From the seed to the business, we can connect. So the 47 private companies first draw a roadmap of this material system. They imagine the new electric vehicle, trains, airplanes operated by motor, driven by motor, and also long-distance microwave power transmission and 5G wireless communication. In order to realize this system, we need a new device. And in order to realize new device, we need the fundamental crystal growth technology. It's a backcasting approach. So we built a new clean room in our campus. It's an open platform only for gallium nitride on gallium nitride process line. I think it's only one for especially designed to GaN-on-GaN process line. And the director is from academia, but the sub-director, he is from Toyota, and he is from Denso. These industry people support us to operate the new clean rooms. It's an under one roof concept. So 47 companies asked us for DPV LEDs, new type of displays, and the power assist robot, electric vehicle, trains, the motor-driven aircraft, microwave energy transmission, and 5G communication. In order to realize that, we need a new modules. And to realize new modules, we need a new device. And for new device, we need a new technology for fabrication. It's a backcasting approach in under one roof in our campus. And once some new things can be found from the bottom side, we instantaneously realize the commercialization. Let me explain. This is our new display. This is our new display chip. It's 1 millimeter by 1 millimeter, but it's 8 by 8. So this is very, very efficient. We don't need to use the filter. Okay. So it's at least 4 times higher than that of the conventional smartphone that you use. And this is the wafer LED technology. It's not a chip, the assembly technology. So it's very cheap. So to realize such a new systems, the academic staff were joined. We have experts in materials, and we have experts in optical device, power device, wireless device, and circuit, and process technologies, packaging. So all of us are waiting for you to join. So if you are interested in our activity, please visit this site. Unfortunately, still it is written in Japanese, but we are preparing the English version as soon as possible. Okay, that's all. Thank you so much for your kind attention.